Hello, welcome to another Stat 510 video. This video is sort of humorously going to be titled All of Statistics. Obviously, we're not going to talk about all of statistics in this video. What we're going to talk about is sort of everything we've done in this course, maybe at a slightly higher level, maybe making some comments that'll help solidify some of the things we talked about. It's also, a reference to the book we're using, which also has this sort of ambitious title. Maybe some thoughts on that at the very end. Okay. So I've referenced this picture a million times at this point, but just to start things off, I think this is sort of the picture that describes, really what it is that statistics does. And in particular, we have some data, and we want to learn something about the world. The world being the thing that generated the data, except we don't know exactly how that process works. That is, we don't know how to go from like the underlying world that we live in and exactly how it generated the data. If we did, we could analyze that data through probability, but in the real world, often we have data and we want to sort of infer things about the world from that data. We still need the rules of probability there, but now we're sort of using the rules of probability based on a set of assumptions and a sampling distribution and things like that. Okay, so one question that I don't know if we talked about in this class is, what is statistics? Normally we'd be in person and I would do this in a lecture setting, and there would be kind of a joke here because someone will inevitably say some very nice answer about it's the study of the collection, the manipulation, the organization, analysis, communication, etc. of data. They'll say that magic word data, and great. But then I'll come back and say, well, actually what statistics is the study of statistics. That sounds incredibly circular, which it kind of is, but here, what is statistics refers to the field of statistic, but in my answer here, the study of statistics, a statistic is a statistic, the objects that we have been studying in this class. So the next sort of logical question is to say, well, what is a statistic? Well, a statistic is a function of data. So a statistic is this thing where you input data to it and it creates an output, which is usually some sort of number. This definition is sort of just sort of casual. Technically, you need to say it's a function of observed sample data, yada, yada, yada. But generally, that's the idea, right? So we have some data, and we apply a statistic to it, and it outputs some number. Realistically, we'd like that number to be something useful, and that's kind of where we're going with this. But realistically, anything that takes in data and outputs a number is a statistic. For example, my favorite statistic is you show me some data, I run it through my statistic, and I output the value 5. No matter what data you show me, I output the value 5. Is this a statistic? Yes. Is it a useful statistic? No. It's only useful in that it shows that, all a statistic does is it takes in some data, outputs something, usually a number, and we can analyze how good they are. I don't need to do a lot of analysis of that particular statistic. It's just bad. Unless you're trying to estimate something with the value 5, but how would you know that ahead of time? Okay, so this notion of a statistic often gets a little bit confusing because statistics often play sort of two roles simultaneously. So I've written the same statistic twice, and I've sort of been very clear about, so T here is what we're calling the statistic, and I'm writing it as a function with the input being the data, the x1 through xn. We very rarely actually do that in practice. We normally obscure that part and move right to something like this where it's the definition, and a lot of times we'll call this one x bar, and I'm going to call this one big X bar. So the only difference between these two lines is that in one case I'm using little xi's, and in the second case I'm using big xi's. So this is a sample statistic. So it's assuming that we're going to input some actual numbers for the xi's, and it's going to crunch the numbers and output a single value, right? So a statistic will take in data and output a value of the statistic for that data, right? And so we understand that for different data, it will return a different value. And in understanding that, we go, oh, that's interesting. Let's study that idea. So if we go a step further and sort of make some potential assumptions about that data, that is, we replace the individual data points with random variables and we assume distributions about those. Well, now, using the capital letters, this is a statistic, but it's also a random variable. And we can analyze this to tell us basically, first and foremost, the distribution of this statistic. Because until we see the data, the randomness of the data carries forward to the statistic, and this X bar here, the capital X bar, will have a distribution. In practice, you wouldn't know it, you might estimate it, but in probability and mathematical statistics, we can analyze the distribution of that statistic. But so maybe something I'll mention here is, so when we're thinking of statistics this way, we're often doing data analysis. This isn't a hard and fast distinction. There, sometimes it's blurry, but here when we're dealing with random variables, then we're more so doing mathematical statistics. So, sometimes the lines are blurred there, but generally, if you're working with data and trying to analyze a particular data set, you're obviously dealing with sample statistics. Now, you're potentially leveraging the mathematical statistical results about it as a random variable, but in that moment, you're not doing any sort of mathematical statistics. You're just calculating a statistic. Okay. So a big part of what we do is use random samples. You don't always have the luxury of a random sample, and there are, fields of statistics that deal with that. But a lot of times, especially in first presentations and courses like this about mathematical statistics, we're often assuming a random sample. So this line here, what it says is that x1, x2, blah, 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 xn, those are a set of random variables that all are sampled from some distribution f. Generally, this tilde here implies identical distribution, because we're literally writing it as all the same, and it generally implies independence. It's not always 100% true, but generally if you see this and it's not clear that there's dependency or different distributions, you can kind of assume the data is IID. Or assume that we're assuming the data is IID. So something we did in this class is we said, well, we want to learn this thing. So that's one of the sort of fundamental tasks, right? You have some data, you want to infer the distribution that data came from. And sort of one of the first ways we looked at doing that was through the empirical distribution, and that was sort of our first pass at doing something like that. But what we've been doing more recently was something like this. Say, okay, I have some random sample, and now I'm going to assume it's IID from some particular distribution, let's say normal with mean mu and variance sigma squared. So now we assumed a lot of things about the distribution that generated this, and now, instead of learning the whole distribution, we simply want to learn the parameters. Because if we learn the parameters, then the whole distribution is specified, and we also know the distribution. So there are two different ways of doing the same thing. The first, when we did it non-parametrically with the plug-in principle, that has the nice property of not having to make any assumptions. But I think something you may have noticed when we said we did sort of downstream things like make confidence intervals. They're always really wide because we're not making a lot of assumptions, so we have a lot to go on. But if we can make an assumption, then we can boil down the learning process, learning the parameters, and oftentimes certain things become easier, like say making confidence intervals, you might get shorter intervals, but those shorter intervals are dependent upon the fact that you assumed the correct distribution. Something we didn't talk a lot about in this class is, well, when you're making those assumptions, how do you check them? That's something that's generally talked a lot about in more modeling-based classes, but realize that anytime you make an assumption, that's sort of like a threat vector for your model. Like if that assumption's bad, it'll have downstream effects on everything you're doing. So that's just something to keep in mind. Always question your assumptions. That's the number one way models can go bad. Okay, so a few slides back I mentioned a statistic is just a function that takes in data and outputs some number. And I gave this example of just outputting 5 always. And we sort of realized right away that like that's probably a bad statistic. But why is that a bad statistic? Because a lot of times the statistics we care about are statistics that are quote unquote estimators. That is, a lot of times we say, well, there's some unknown value, let's call it theta, that we want to learn about. And so what we're going to do is develop a statistic here, g of x1, x2, xn, and we're going to call that an estimator for that theta. Again, anything can be an estimator, but now, because now we've given the statistic a sort of goal, we can better evaluate, oh, is the statistic good or bad? I had a note to myself to say, okay, yeah, so all an estimator is, it's a statistic used as what I'm going to call a quote-unquote good guess for, in this case, theta, right? So, I mean, realistically, any statistic can be evaluated as an estimator for that theta, but, you know, some could get thrown out immediately. Like, let's say we were estimating P, the probability of a coin being flipped heads, and I give you an estimator that always outputs the value 5. You can right away just discount this because it's not even producing values in the potential range of things you're estimating. That is a probability that would only be between 0 and 1. So just kind of something to keep in mind there. Okay, so an idea that I think I've maybe mentioned before, and if not, I've been subtly hinting at is, so this is not a technical definition, but what I like to say is that parameters are to a distribution as an estimator is to data. So generally, we can sort of think of parameters as some function of a distribution. And when we were talking about the plug-in principle, we kind of did that directly. So we would say that theta is some function of the distribution. And what we did with the plug-in principle was literally say, okay, well, to develop an estimator, what we're going to do is we're going to take that function and now apply it to, in that case, the empirical distribution, and that will be sort of one way to create an estimator. Okay, so obviously there are many other ways to do this, which we've discovered, but this one, in particular, the plug-in principle, makes this sort of relationship very obvious, right? So like if you wanted to estimate the mean of some distribution, well, the sample mean is sort of the obvious estimate for that, and so on and so forth. Okay, so then we come to this question of, okay, well, I developed this estimator, and maybe I even used a reasonable way of obtaining it, say the plug-in principle. How good is it? And sort of the metrics we generally looked at were these ideas of bias of the estimator, variance of the estimator, and putting them together, the mean squared error of an estimator. And hopefully in this course, we've sort of convinced you that while, you know, we'd like an unbiased estimator, in particular, we'd like an unbiased estimator with the lowest possible variance, we've found that sometimes if you sneak in a little bit of bias, it reduces the variance in a way that actually reduces the mean squared error, making it a good estimator. This is often referred to as the bias variance trade-off inside of machine learning. So this is hopefully a concept you've seen a number of times already. Something we did much more recently is we sort of generalized these ideas. So in general, if we move to a more decision theoretic way of thinking about things, instead of thinking about bias, variance, mean squared error, we would think about things like loss, things like risk, and things like admissibility, if I can spell it. So it turned out that under squared error loss, the risk just ends up being mean squared error. So we were sort of always doing these things without knowing it. But now we can sort of think about, oh, there are a lot of different ways to evaluate an estimator, which basically says, you know, like on average, how much loss is this estimator being exposed to? Okay, so, you know, these things tell us, well, how do you evaluate an estimator? But often we have to say, well, how do we actually get to an estimator, right? We can't just like make these things up at random and then evaluate them. We want sort of principled ways of doing this. So we looked at a number of them. I just mentioned the plug-in principle. That's sort of, in my opinion, the most basic, and it really highlights the whole process here. Like first estimate the distribution, and then use that to create an estimator for a particular parameter. We also looked at maximum likelihood. The idea that you want to match the likelihood to make your data as likely as possible to have come from that distribution. So that's another generally principled way of developing an estimator. We looked at method of moments, where you match the sample moments to the population moments. And sort of more recently, we looked at Bayesian inference, which sort of took this idea of likelihood, but then also brought into it priors, where you as a person with degrees of belief about something can mix those two concepts together to get a posterior distribution for a parameter and thus create point estimates that way. So I should also note that along the way, part of the reason that these are such established ways of doing things is, one, we sort of walked through the natural reasoning behind why you would do them. But then two, statisticians have spent a lot of time studying these things, right? So they have various, sort of downstream properties, right? So we looked at things like, with the plug-in principle, we sort of asked the questions like, is it unbiased? How much variance does it have? What's the mean squared error? Is it consistent? With the maximum likelihood, we did similar things, and we even said like, oh, asymptotically, it has these certain distributions, which worked out to be really nice, because then we could do other things like interval estimation and hypothesis testing. So that's I'm going to circle back to this point, but so one, you want to find ways to create estimators, but then two, you want to really understand their properties. So, and then we've sort of hinted at this already. So, okay, great, we have these estimators. And so the first thing you do is like, I have an estimator, it creates a point estimate. And that is like, our quote unquote best guess for the value of the parameter. But we realize, or at least I hope we realize, that those point estimates are variable based on the data we receive and are able to analyze, but the parameter is fixed. So what we realize is that variance in the estimator, we should probably factor that in when we're doing the estimation. And that's when we move to things like interval estimates, or sort of obviously very related, the idea of a hypothesis test, like, hey, is the parameter this value or not? And that'll take into account more than just, hey, does the point estimate match the true value of the parameter? It'll say, does the point estimate match the true value of the parameter, plus or minus some noise. So those are sort of the three main tasks that we've talked about. A lot of things in statistics that you might not even think about this way are these things, right? So, for example, in machine learning, we often think about, we fit some model to some data, we get some new data, we make a prediction. Well, that prediction is just an estimate of a particular quantity, and we can evaluate it through that lens, and that's what statisticians do. Okay, so I want to make a note on standard errors and sort of what they are, and a few things that I think are confusing, and this is a concept that I will probably in some ways test, or quote unquote test on the final exam. So a lot of times we want, what I was just saying, with an interval estimate, we can have some theta hat that estimates theta, right? But often we want a confidence interval. So one of the ways to do a confidence interval is something like an estimate plus or minus a standard error. There would be some constant, like a critical value in front of it, but I just want to get to the idea of it's confidence interval plus or minus something that measures variability about that statistic. So, but the thing to realize is that the standard error, actually I might even put this in quotes, is sometimes a confusing thing, because I think as a community, we don't have a strict definition of it. We kind of use two definitions simultaneously, and I want to key on that for a second. So, because we understand that a statistic, before we see the data, is random, we can talk about things like its expected value, its variance, its standard deviation. And those things, which I have written here, those depend on the distribution of the statistic in question. So, actually, it depends on, right? Okay. So, and obviously, this is really just because theta hat is a function of the random variables. What did I say? Yeah, the theta hat is a function of the data, which can be viewed as random variables. So it ultimately depends on the population distribution, but specifically in this case, we're thinking like, okay, this depends on the distribution of theta hat. But so something you should realize is because these quantities depend on that distribution, a lot of times if we don't, like for example, okay, so theta hat depends on the population distribution. Well, the population distribution we don't know, so ultimately the distribution of theta is going to be some function of the unknown parameters of that distribution, and so are these two quantities here. So for example, like if we looked at the expected value of one of our most common estimators, x bar, right? That's actually mu, right? So we can't really know that ahead of time. And sort of in a similar vein, the standard deviation of x bar is sigma over square root of n, right? So while the standard deviation of x bar is specifically like a measure of the variability of that statistic that could be useful for developing a confidence interval, well, if we don't know this sigma, we can't make an interval with that because we want to plug in a number. We want to get two numbers as the endpoints of our interval. So what do? Well, we estimate that quantity, right? And so that's what this last thing here is, the estimated with the hat standard deviation of the estimator. But this, in addition to depending on the parameters, it depends on the distribution of theta hat, it also depends on the estimates of the parameters. Sort of assuming we're doing this parametrically, but yeah. In this case, instead of using the standard deviation of x bar, we would use the estimated samples. We would use the estimated standard deviation of x bar, which instead of sigma over square root of n, we would plug in some estimate for sigma. So where this gets to be, in my opinion, incredibly confusing is that some people refer to the standard deviation of theta hat as the standard error. Some people refer to the estimated standard deviation as the standard error. This is one of the many notationally nomenclature. It's one of the many notations or nomenclatures in statistics that are just incredibly confusing because we do this to ourselves. But so I would just note that in the book that we're using, it does sort of delineate these two concepts with standard error and estimated standard error. If I could rant for a moment, I personally do not understand why we even need the standard error nomenclature. Why we don't just call it a standard deviation. I would genuinely like to hear answers to that question. I don't know. Obviously, smarter people than me developed this field and named these things, but this one I just always found confusing. Maybe it's confusing because I'm not smart enough, but I don't know. I don't feel like that's super helpful for especially people that are learning this stuff. So in my mind, anytime I hear standard error, I just replace it with standard deviation, and I know that like, well, hey, if I'm making an interval, I probably need the estimated one, and so on and so forth. But that's I don't know. Maybe I'm crazy. I guess the only reason I can think for why this is that standard deviation is just saying like, oh, the variability of the estimator. It's literally just an expectation basically, right? But the name doesn't really imply any sort of thought of this being related to estimation. Where a standard error, okay, so now since we're estimating something, it's an error, but like, I don't know. I'm really splitting hairs there. What's the difference between an error and a deviation? I don't know. So, yeah, I don't know. I find that confusing, and if I hadn't said it already, maybe I said this back in a video a long time ago when we introduced this, but I think that's confusing, and I think that really trips people up, but hopefully this helps explain that a little bit. Okay, so I think maybe wrapping this video up, what is mathematical statistics, right? So we said what statistics is, and then everything we've talked about from now to then is doing mathematical statistics, but I want to maybe talk about it at a more abstract level for a second. So, I think a lot of, from a student perspective, I imagine what mathematical statistics feels like is some jerk professor, this guy, gives you some homework exercises, and you manipulate these statistics to come up with an answer to the question, and a lot of it seems kind of silly because it's stuff that you could just look up, like, hey, derive the MLE for this parameter of this distribution. It's like, well, that's just on Wikipedia. Like the derivation, you can find it there. You can find the estimator. You can just look it up, right? But so the reason we have you do those things is because there's certain skills that you develop in doing so, certain intuitions you develop through going through those processes. At least we hope. Maybe we're not doing the best job at that. But so taking it a step further, so like, what would someone who is a working academic statistician do with these things, right? So, and again, this might sound ridiculous, but so if statistics is the study of statistics, one of the what I would say is one of the main goals of a lot of statisticians is to develop new statistics. A lot of times they'll call that methodology or methods, but ultimately what they're doing is creating new statistics, or potentially finding better uses for existing statistics, or things of that nature, or finding new situations where older statistics apply. But ultimately, we're looking for, okay, here's a situation. We want to estimate something or know something about the world. What statistic will do that for me? That's kind of like a way a lot of these problems, a lot of these new methods come about, right? You have some new situation that you haven't encountered before. You want to estimate or learn something. Well, let's come up with a new statistic to do that. So that would be sort of, in my opinion, one of the mainline goals. And then for either one of these new statistics or an existing statistic, a lot of times we want to then spend a lot of time understanding their properties, right? So what is, for example, like, what is the sampling distribution of that statistic under various population distribution ideas? And then sort of like, well, okay, so what are you trying to estimate with this thing? And then how good is that estimation? Again, under like a variety of population distributions, et cetera, et cetera. And ultimately, what you're doing in doing so is you're starting to like develop an argument of like, oh, this statistic should be used in practice in these situations. That's ultimately what, in my opinion, the statistical literature is about. It's saying like, okay, here's a statistic, here's when and why you should use it. And I hope something we've done in this class is started to especially hint at this notion of one of the big parts of this life cycle here that we're talking about is simulation, right? Because to understand a statistic, one of the ways we can do that is say, okay, well, let's sample from some assumed population distribution, look at our statistic, and compare to the true value of what we're trying to estimate, because again, we define the population distribution. And then, I would say a lot of what graduate students in statistics do, that is PhD students working on research with their advisor, is they do that. They spend time on a computing cluster just running a ton of simulations to say, okay, how does my method that I develop work under all these different situations? Sometimes mathematically you can derive those things, but even if you can derive it mathematically, it often helps to gain some intuition, like as a first pass, like, hey, does this work at all, by running a simulation study? So hopefully you didn't find all the simulation we did in this class sort of obnoxious, and hopefully you're starting to see that connection of like, we can understand the statistics we're using by literally just setting up scenarios and seeing how well the statistic does. That's my favorite way of doing this, because I'm not particularly good at math, which is maybe an irony of me teaching a mathematical statistics course. But I think it's important to know the tools you have to sort of accomplish these tasks. And I think if you understand what's going on and then applying simulation, you can really get pretty far with that. Okay, so I think that's all I had for that. Yeah, so hopefully this gets you thinking about it a little bit. But if you have any questions sort of about the larger nature of statistics and questions about it, feel free to pop into office hours to chat. Oh, I was gonna make reference to the title of the book, All of Statistics Again. So if you kind of look at what happened in terms of what parts of the book, so there's parts, like, so for example, there's three parts, right? If you look at the index, the first part was probability, and we spent some time on it, but not a ton, because hopefully a lot of that was review, and ultimately we wanted to talk about statistics. So the second section, which we also covered in full and spent more time on, was statistical inference, right? And that was the goal of this course. But what I want to mention is that there's a third section of this book called Statistical Models and Methods. And it has the sort of methods, i.e. statistics, that you would often use in the real world. So things like linear logistic regression, talks about multivariate modeling, inference about whether or not things are dependent, causal inference, and then it starts talking about some things like nonparametrics and smoothing, and then a little bit about classification, in kind of a machine learning type thing. So why am I mentioning this? Is because you now have access to this book. Either you bought a hard copy or have the free online version through the library. And part 3, where all these things live, I think it'll be a nice reference for you going forward. I think one is you could read through it yourself with the knowledge you gain in this course, and I think be successful sort of self-studying some of these things. But the other thing I would mention is I find it to be useful for sort of, how do I explain this? Sort of like, just like really locking in your learning. So a lot of those things I just mentioned are things that you might learn in other classes. But I think sometimes it helps to see things from different perspectives. So like, you'll take a class on regression from one professor, but I think it helps to have received multiple explanations for things. And I think I appreciate the style of this particular textbook. So what I would say is, maybe after your regression course, come back to this book and read through the chapter on linear and logistic regression. And I think you'll just start to pull out more pieces and build in that bigger picture of how everything fits together. That's an exercise I do all the time. Is I'll get some new book like this, and for me it's like I'm not gonna read through this equation by equation, word by word, because I've seen all this material before. But say I'm about to teach linear regression again or something. Well, it might be useful then to go find that section and read through it, and you'll do this thing where you nod, you go, okay, I know that, okay, I know that. And then you'll see something and you're like, oh, this is familiar, but I didn't really get it that first time. But now, because I've seen more things and I'm coming back to it with slightly fresh eyes and a new explanation, you go, oh, now I get it. So I have that moment all the time where I'll be sort of skimming something that I need to refresh my memory on. I'll get to something and be like, oh, I get it now. And then I think I find that to be a rewarding experience. And I think one note there too is I think you'll find that when you first sort of start learning these things, which a lot of you are probably just doing as you're starting, say, a master's degree, like maybe you didn't do statistics previously, or a lot of times when you're an undergraduate you don't fully understand everything the first time through. So you're really starting your, I think as graduate students, you're really learning on your own, and we're just here to help you. I think undergrad is slightly different. But I think that process is very frustrating at first, because you'll flip to a random chapter here and go to review it, and you'll be like, I kind of remember that, and you don't have, you kind of haven't put all the puzzle pieces together yet. But every time you sort of lock in another piece and better understanding, when you review that chapter, you find yourself nodding and going, yes. And then you get to that one thing and it really sticks out, and you have a better time sort of like lasering in on that and now understanding it. So all that to say is that I think the whole concept of like you have a foundation and now you're doing self-learning, it's very daunting at first. But over time, it gets easier and easier because you just have more pieces of the puzzle put together. I mean, I guess the analogy is if you've ever done a physical 500-piece puzzle, the first pieces are impossible, right? Because you got nothing to go on. There's no sort of scaffolding. There's no boundary set. There's no like adjacent pieces that you can do pattern matching with. But once you have a lot of the puzzle in place, adding that next piece is easier because you have all this stuff around you with contextual clues and things like that are helping. I'm really rambling now. That might be a strained analogy, but I do want to encourage you to start relying on yourself a little bit more than classes. That's something my expectation of this course is that, to me, it's not about you learned this particular concept, you learned that particular concept. To me, it's about hopefully establishing a foundation and really keying in on some of the key fundamental ideas of statistics to give you that base and some of those correct understandings and intuitions so you can start pulling various pieces of the puzzle together. Actually, I'll maybe try to wrap this up and say, because there was sort of some discussion in the class about like, oh, what should the last topic be, right? And if you looked at that Piazza post, there were all sorts of different suggestions because we all have different interests, and that's totally cool. But I would encourage you to really, maybe find the chapter in this book and go through it and research it on your own in general. I would encourage you to do that, to really be like, okay, I'm going to try to dive into this topic a little bit myself, and hopefully you'll find that the things we did help with that. Maybe if you found some of the things we did here are helpful with that, let me know, because I'm always interested in that kind of thing. But I really do think that, once you've sort of gotten to this point where you've started to see some of this material at the graduate level, honestly, the next step is trying to be like, okay, let's test what I know by going out and trying to, learn this new thing on my own and see if my foundation can allow me to do that. Because that is, in my opinion, that's the ultimate goal for us as educators. Would it be nice if you all got A's in the class? Yes. Would it be nice if you got the final exam 100% correct? Well, yeah, because then it's a lot less grading for us because it's easier to grade correct answers. But none of that matters to me. What matters to me, honestly, and it's hard to do, and I generally don't know if I'm doing a good job of it, is like, am I teaching students in a way where they can carry this forward and use it to be self-directed learners? Because ultimately, school is going to end. Even if you go for a PhD and spend 5-ish years on that process will end, and your whether or not you go that route, even if you do after master's, you're already starting to venture into territory where you're going to be expected to learn some things on your own, either at a job or in a PhD program, or especially after a PhD program. So it's scary, it's daunting, it's especially frustrating when you're just getting started. But I think it's worth diving in and spending some time trying to do some of those things. Okay, I have really been rambling now. So if you made it to the end of the video, what is my line? If you made it to the end of the video, good job, and I will see you in the next one.